Chapter 10, Lesson 3, page 293. We're going to begin studying momentum. But before we jump into momentum, let's see what we've learned so far in Lesson 1 in Chapter 10, all about motion, and in Chapter 10, Lesson 2, all about acceleration. We begin by reviewing what we've learned so far. What is acceleration? Acceleration is the change in velocity divided by the time it takes for that change to occur. Remember, it happens in three different ways: speeding up, slowing down, or if there's a change in direction. Number 2, how is positive acceleration drawn on a speed versus time graph? And probably answer number 5 right away too. What does a horizontal line show on a speed versus time graph? To answer number 2 and number 5 of our review, you should probably go to page 292 and take a look at the graph. Positive acceleration is drawn with an upward positive slope. Negative acceleration is drawn with a downward slope. So the positive acceleration would be part A on the picture on top of page 292. And then the downward slope would be part C. That's where it's negative acceleration. And for number 5, what does horizontal line mean? Where it's going across at the top. That means that the object isn't actually accelerating. It's going at a constant velocity. So for example, you getting on the highway, you're going to speed up on that on-ramp, get to the cruising speed. Maybe you get on the highway and you click on cruise control, and then you're going to stay at that constant velocity. If you're going to change lanes or then have to slow down for some reason, that's where you might have that downward slope. But positive acceleration is a positive slope. Negative acceleration is going to be a negative slope. And if it's a straight horizontal line, that means you're at a constant velocity. Number 3, is negative 4 meters per second east a description of positive acceleration or negative acceleration? Well, the negative symbol here means that it's negative acceleration, which actually means that the object is slowing down, not that it's going in some type of mathematically negative speed. It's slowing down. Number 4, what is the equation to solve for acceleration? When you're solving acceleration, you have to take in two factors of speed because there's a change that's happening. There's final speed and there's initial speed. You're going to subtract final speed from initial speed to figure out if something has gotten faster or slower. That's what you get your negative symbol from. If that initial speed is slower, you're going to subtract those two. So it's final speed minus initial speed. You take that difference and divide by time. That'll give you your acceleration over the course of that time period. Number 5, we already answered with the look at that map. Jump into our lesson for today. Today we're going to define momentum, explain why momentum might not be conserved after a collision, and predict motion using the law of conservation of momentum. Collisions. A collision occurs when a moving object collides with other objects. What happens when a cue ball collides with another ball in the game of pool? The answer is that the velocities of the two balls change. The collision can change the speed of each ball. The direction of motion of each ball, or both, when a collision occurs, changes in motion of the colliding objects depends on the mass and the velocities before the collision. A collision is a moving object running into another object. Based on the mass and the motion or velocity of that object, it will determine how that collision takes place. Mass and inertia. The mass of an object affects how easy it is to change its motion. Here's our definition. Mass is the amount of matter in an object. Imagine a person rushing toward you. To stop the person, you would have to push on him or her. However, you would have to push harder to stop an adult to stop a child. The child would be easier to stop because it has less mass than the adult. The more mass an object has, the harder it is to change its motion. In figure 12, the tennis ball has more mass than the table tennis ball. Again, mass, the amount of matter in an object. A table tennis ball, which is a ping pong ball, has less mass than an actual tennis ball, as in one of those is heavier. That's kind of a way in which we understand it, but mass is the amount of matter in that object. The tennis ball has more mass than the table tennis ball or ping pong ball. A big racket rather than a small paddle is used to change its motion. The tendency of an object to resist a change in its motion is called inertia. The amount of resistance to change in motion increases as an object's mass increases. So mass is the amount of matter in an object. Inertia is the tendency of that object to resist a change in motion. For example, here's a good way in which you can remember inertia. If I want to open a door, I turn the handle and pull the door open. I can move the door. If I wanted to move the wall, I couldn't move the wall. The wall has way more inertia than the door because the wall is resisting movement. It doesn't want to change its position. It doesn't want to go into motion. Obviously, buildings are built so that they don't move, right? So inertia is the tendency of an object to resist a change in motion. If you've ever seen somebody lifting weights or you've tried to lift weights yourself, the heavier you're trying to lift, the heavier the object that you're trying to lift, the more difficult it is to lift that object. That's our definition of inertia. Tendency of an object to resist change based on the amount of mass that it has. More mass means more inertia. Take a look at these items and compare. What's more difficult to move? If you had to pull this semi-truck, could you? Probably not. It's super, super heavy. Some of the world's strongest men have competitions in which they try and pull these things with their brute strength, and they're able to do it, but that's because they're the strongest people in the world. What's more difficult, moving a bowling ball or a basketball? Well, there's a reason why we bowl a bowling ball and we shoot a basketball in the air, because this is rubber filled with air, and this is a really solid, heavy, couple pounds bowling ball, right? This has more mass, therefore more inertia. This has less mass, less inertia, means it's easier to move. How about a feather? Opposite of a semi, right? Really easy to move because it has a little bit of mass. It doesn't have much inertia whatsoever. Momentum. You know that the faster a bicycle moves, the harder it is to stop. Just as increasing the mass of an object makes it harder to stop, so does increasing the speed or the velocity of the object. The momentum of an object is a measure of how hard it is to stop the object, and it depends on the object's mass and velocity. Momentum is usually symbolized by the letter P, and it's calculated in the equation momentum equals mass times velocity. So momentum and inertia are almost opposites of each other, because inertia is the resistance to move. Momentum is measuring how hard it is to stop the object that is already moving. Mass is measured in kilograms, and velocity has units of meters per second. So momentum has units of kilograms multiplied by meters per second. Also, because velocity includes a direction, momentum has a direction that is the same as the direction of the velocity. At the bottom of the page, it asks us to practice calculating momentum by taking in the application, the applying math section. It says calculate the momentum for a 14 kilogram bicycle traveling north at 2 meters per second. Well, in order to do this, you're going to take the mass and multiply by the velocity, so you multiply 14 times 2. 14 times 2 is 28 kilograms per meter per second. Okay, so you just simply multiply mass in kilograms times the velocity. Number 2 says a 10,000 kilogram train is traveling east at 15 meters per second. Calculate the momentum of the train. Obviously, thinking about a train and how much mass it is, how heavy it is, you're thinking the ability to stop that train is going to be a ton of energy. So the momentum to stop this is, or the energy to stop this is what we're defining here, or finding is the momentum. 10,000 kilograms times 15, which is going to be 150 units in terms of the momentum. That's in kilograms, again, kilogram meters per second. As a crazy amount of momentum, because the train is so huge and so massive, it's really difficult to stop. So it makes sense that its momentum is a really large number. The conservation of momentum. If you've ever played billiards, you know that when the cue ball hits another ball, the motions of both balls change. The cue ball slows down and may change direction, so its momentum decreases. Meanwhile, the other ball starts moving, so its momentum increases. In any collision, momentum is transferred from one object to another. Think about the collision between two billiard balls. If the momentum lost by one ball equals the momentum gained by the other ball, then the total amount of momentum doesn't change. When the total amount of momentum of a group of objects doesn't change, momentum is conserved. So the energy is being put from one object that you're hitting with the cue stick into the cue ball, and that cue ball is hitting another ball on the table. That momentum is changing from those two different objects once that collision takes place. According to the law of conservation of momentum, the total momentum of a group of objects remains constant unless outside forces act on the group. The moving cue ball and the other billiard balls in Figure 13 are a group of objects. The law of conservation of momentum means that the collisions between these objects don't change the total momentum of all the objects in the group. Only an outside force, such as friction, which is what they experience as the balls are sitting on the table, can change the total momentum of the group of objects. Friction will cause the billiard balls to slow down as they roll on the table, and the total momentum will decrease. The different types of collisions. Objects can collide with each other in different ways. Figure 14 shows two examples. Sometimes objects will bounce off each other, like the bowling ball and the bowling pins. In other collisions, objects will collide and stick to each other, as when a football player tries to tackle another. To visualize this, we're going to take a look at page 296 and 297. Using momentum conservation. The law of conservation of momentum can be used to predict the velocity of objects after they collide. To use the law of conservation of momentum, assume that the total amount of the colliding objects doesn't change. For example, imagine being on skates when someone throws you a backpack. The law of conservation of momentum can be used to find your velocity after you catch the backpack. Suppose a 2 kilogram backpack initially has a velocity of 5 meters per second. Your mass is 48 kilograms, and initially you're at rest. Then the total initial momentum is calculated by taking the momentum of the backpack and your momentum and putting those two things together. So 2 kilograms at 5 meters per second plus 48 kilograms at 0 meters per second to give you a total of 10 kilograms per meter per second. Remember, momentum is the measurement of something's resistance to movement. After the collision, the total momentum remains the same. Only one object is moving. Its mass is the sum of your mass and the mass of the backpack. You can use the equation for momentum to find the final velocity. So in the picture, it shows one student with rollerblades on, and it shows another student who's throwing them a backpack that has some type of weight to it. When the person with rollerblades on catches it, they're actually going to move because the backpack has weight and is going to push them in the direction that they're traveling, that the backpack is traveling. So their motion, their momentum, is now based on the entire mass of the object, so your mass and the mass of that backpack. Because the backpack was moving, it's going to cause you to move in a way. So now look how the total momentum changes. After the collision, the total momentum remains the same, and only one object is moving, obviously you and the backpack. It is mass and the sum of the mass of the backpack. You can use the equation to find the momentum and the final velocity. Here, you have the mass of the backpack and your mass times the velocity, which is calculated to 0.2 meters per second east. So even though you didn't move a lot, you did move because that backpack has weight and mass to it, and it causes you to move because you were standing still. This is your velocity right after you catch the backpack. The velocity of you and the backpack together is much smaller than the initial velocity of the backpack. So because you weigh more than the backpack, you slowed down the backpack and basically brought it to a stop. It moved you a little bit because you're obviously wearing rollerblades to reduce any type of friction, but when that collision occurs, the biggest factor to understand is whichever one has more mass is usually going to be the one that has the biggest effect on the collision itself. Figure 16 shows the results of collision between two objects that don't stick together. If you've ever played marbles, in figure 2 and page 297, it shows what happens when the different types of objects collide with each other at different sizes. In letter A, it says, here a less massive marble strikes a more massive marble that is at rest. After the collision, the smaller marble bounces off in the opposite direction. The large marble moves in the same direction that the small marble was initially moving. Something that's really big at rest gets hit by something small. It doesn't have that big of effect or that big of motion or movement. In letter B, here a large marble, something with a large amount of mass, hits something smaller. After the collision, both marbles move in the same direction. If something big hits something smaller, it's going to continue in that direction. It doesn't really have that opposite effect. In letter C, if two objects of the same mass hit each other and collide head-on, they're going to bounce off each other and go in opposite directions. If you've ever driven bumper cars or bumper boats, you might know what that's like, because you driving your boat and someone else driving their boat, or bumper car and bumper car, are usually similar in mass. When you hit each other, you simply bounce off rather than have one person beat the other, because most of the time you're going the same speed and they're just around the same amount of mass when that collision occurs. Here's another example on page 298. Colliding and bouncing off. In some collisions, the objects involved, like bumper cars in figure 17, bounce off each other. The law of conservation of momentum can be used to determine how these objects move after they collide. For example, suppose two identical objects moving with the same speed collide head-on and bounce off. Before the collision, the momentum of each object is the same, but in opposite directions. So the total momentum before the collision is 0. If the momentum is conserved, the total momentum after the collision must be 0 also. This means that two objects must move in opposite directions with the same speed after the collision. Then the total momentum, once again, is 0. So depending on the size of the objects when they're getting into some type of collision, determines how the momentum keeps going. If you have a larger object that hits something smaller, that momentum is transferred into the smaller object, and that smaller object is going to keep going in that same direction. If you have a smaller object hitting a larger object, that object is going to bounce off, and the momentum is back into the smaller object, even though it might cause that bigger object to move a little bit, like in the rollerblade example. If two objects are the same size, that momentum is going to be conserved by them running into each other and then bouncing off in the same type of direction. Now, your homework assignment for today has 3 different parts. I'm going to read through those directions so that you have an understanding of what to do on your reinforcement. In question 1, below, a code letter has been substituted for every letter of the alphabet. To find out what the sentence says, use the following key to decode it. In the key, the code letters are shown directly below the letters they stand for. Write the correct letter above each code letter, then read the sentence. So you have the first line that's on the top of the page that has A, B, C, D, E, F, G, H, I, J, K, L, goes through the entire alphabet. Below that is the code letter. So in the key, the code letters are shown directly below the letters they stand for. So in number 1, it says H-O-G, hog. That's obviously not what we're looking for in terms of the scientific explanation here. So you have to find the H on the code letter, find the H on the bottom, and then go up to the actual alphabet. So the first one is an H. If you find H on the second line and move up, it represents T. Next, I'm going to find the O on the bottom set of letters. I go up, it's an H. Next, I find a G, I go up, it's E. So the first word, H-O-G, actually stands for the. Notice again how I found that. The second line of letters has L, V, Y, Q. I'm starting in that second line, and then I look up above it to see what it's actually representing in the alphabet. It's written in a code, so there's going to be a little deciphering in order for you to figure that out. Number 2 says, what's the law that is stated above? Maybe that's a giveaway into terms of what you're looking for, as in the law of conservation of momentum that we learned about, but you'll have to decipher that as you follow those directions. In the second portion, the directions say correctly complete each sentence by underlining the best of the 3 choices in parentheses. So you can either underline or circle numbers 3, 4, 5, and 6. And then for extra credit today, we're going to take a look at numbers 7, 8, and 9. Number 7 says, answer the following questions on the lines provided. You've got a 500-gram model train traveling at 0.8 meters per second, colliding with a 300-gram stationary car. Cars hook up and move off down the track together. How fast are they going? You have to try and find velocity from the momentum that's taking place with these 2 objects that are now colliding and then moving. Okay? So 7, 8, and 9 are extra credit. Do your best to answer those. Numbers 1, 2, 3, 4, 5, and 6 are your actual homework assignment. God's blessings.